Okay, so this is a long time ago. We were here. So we were about to see our first denoising algorithm. And this denoising is aimed for uncorrelated noise. And we were discussing what was uncorrelated noise, what were the sources of uncorrelated noise. So uncorrelated means that whenever you know the noise at one point, you don't know anything else about nearby points. And we can make an example here. So okay, so let's say that this is x of t, this is t, and then we have, this is a random noise, but you may agree that this is, given that, let's say that you have a value here, you know that the nearby values must be somewhere close. Okay, so they must be somewhere close to these values. Okay, and this is different from this equation, where you have x of t, and then you have completely random. So given a point, it is very hard to say. Given a point, it is very hard to say what is nearby. Okay, and we were encoding that with the autocorrelation. So we were encoding that with the autocorrelation that we formulated in this way. So the autocorrelation right. Vamos checando. Conso, ¿cuál es el colmo de Batman? Que le roben. So this is the expected value of x t as tau. So, you know, I always write the equations in one dimension because they are simpler to write. But you may extend these ideas to multiple dimensions, only that everything, the lag and everything could be a vector. Okay, so the autocorrelation tells you whether something is uncorrelated or correlated. So the autocorrelation of this kind of function would be this one. X of tau. So this is the lag. So it is somehow, so given a point, you know something of the nearby points. While this one is, it is a delta. Okay. So it is a delta. So given a point, you don't know anything about the nearby point. And here you have the reason why. This is called, this is so, I want to deselect like this. So you know that the blue. So the power spectrum density. The power spectrum density of a signal, and the axis is omega, so it is frequency. It is the Fourier transform or the autocorrelation function. Okay, so what is the Fourier transform of the triangle? It's a single square. Okay, so this is something like this. So this is the PSD of the this signal here. And what the analysis is on. What is the power spectrum density of a delta? Y. It's a constant. This is the power spectrum density of this signal here that we said it was independent. Okay, so this is why this kind of noise, here, this kind of noise is called white noise. Okay, this is called white noise because it's a spectrum. Is flat. That is the spectrum of white light or white light, and that comes from an autocorrelation that is a delta. And all these things are on average. Okay, so on expectation. Okay, so let's see, and so. Let us see. Yeah. So here we have, so everything that we have been talking about is the relationship of a point with a nearby point. And so we have a point, let's see here. So we have a point, and we have a nearby point. Okay, but we haven't said anything about the distribution of x. Okay, so we could have so something else is okay. What is these are random variables? If this is a random variable, what is the distribution of x as a random variable? And can be Gaussian, can be uniform, can be whatever. Okay, always label your axis. Okay, it can be whatever, and that is what is discussed here. So we may have noise that is Gaussian, that is uniform, that is salt and pepper. So this is f of x. So given a point, what is the distribution of that point? And the autocorrelation, the fact that it is uncorrelated, it talks, given a point, what can you say about nearby points? And how color Gaussian color noise looks like, and uniform. You see that the aspect is different. So there is more variety here. More variety is, how do you call variety in statistics? It's one of the most typical measures of variety. Variance. So the variance of this distribution is larger than the variance of the previous distribution. Okay, and here is an example, so you know that the histogram is an approximation of the probability density function, and you see, okay, it looks like a Gaussian, but it is not exactly a Gaussian. You have all these little bumps there. So the little bumps are, okay, if you take an image that is really large, then this would be much smoother. Okay. And if you go to infinity large, then it would be exactly a Gaussian. And yeah, and this is the autocorrelation. Now it is a bit more complicated because we have to write the lags for the two signals. So a lag for the two dimensions. So the lag for the rows and the lag for the columns. And we have also talked about this function psi. So this function psi, what it's doing is whenever we have to take a lag, okay? So you take a point at the nearby point. What happens if you go out of the image? How do you measure that? And one possibility is doing this modulus. So doing the modulus makes, okay, whenever you have, let's say that this is a very common tree. This is a very common tree. So it would be, okay. Okay, so we have an image that goes from 0 to n minus 1. Okay, these are the number of columns. And we have this point. And we have a nearby point. And this one is out of the image, but what we can do is to periodize it and put it here. This is the same trick that the Fourier transform is doing, right? You know already, this is one way of thinking of it. The other way of thinking of it is that this image here has been replicated. Okay? So these 2 points are equivalent. Okay, but in terms of coordinates, okay, so this is coordinate x at n minus 1. I want this one, but that one, so let's say that is the point C. How can I say, okay, you have to do the wrapping? So you can compute the modulus of C n. So what is the remainder of dividing C by n? Okay. And the remainder, let's say that C, let's say that C is equal to n. Okay, so you would have modulus of n divided by n, that is 0. Then you are back to the left side. And if you have C plus 1, then that would be 1. And if you have C plus 2, so if you have another point that is C plus 1, this one would be this one. And so on. Okay. So this modulus is this simple trick of making the image periodic. And yeah, it is very well understood when x is positive. When x is negative, you have to add n to make it more clear. It is the same. Okay, so this is on the other side. Whenever you go from the left, you go out from the left, you come back in from the right. Okay, but it is simply this periodization. And then this term here. So this term here is subtracting the mean. This is the mean. So the autocorrelation is defined. I was a little bit. I didn't want to complicate too much the notation here, but in this equation that I wrote somewhere, this one. This is the autocorrelation when the two signals have 0 mean, or x has 0 mean. Okay? If it doesn't have 0 mean, you have to make it to have 0 mean, and this is the way of making it 0 mean. Okay, so you have your signal, you subtract the mean, and by definition it has 0 mean. Okay. And then that is the one that you have to use in the autocorrelation. Okay, good. And here you have a representation of what I said. So let's say that you have white noise. So the autocorrelation is approximately delta. You see that there are little ripples there. So they are not exactly delta. And the Fourier transform is not exactly a constant, but they are pretty close to constant. Okay. Okay, so let's say that that we have a clean image. We have a noisy image, just pure noise. And we analyze what is the power spectrum of these two images. So we will take a profile, because so you know the power spectrum of an image is a 2D signal, but let's take a 1D profile of that one, 2D signal. So this is how the power spectrum of the image would look like. And this is how the power spectrum of the noise would look like. And again, this is not exactly a constant, but if we repeat this process of creating many images, many noise images of the same kind, and we take the average of all those, it would be a constant. Okay, that process is here. So this expectation is only true when you repeat the process infinite times. Okay, if you do it only once, okay, it is close to a constant, but it is not constant. Okay, so we have the power spectrum of the image, the power spectrum of the noise. And now we add the noise to the clean image. And because we are simulating this process, we know exactly which part we are adding from. So if two, okay, so let us count. Okay, so let's say we have an image A that will be an image I plus some noise. Now we study what is the power spectrum of this. So the power spectrum of A, if these two are independent, is the power spectrum of I plus the power spectrum of noise. This is true only. This is true if I is independent of A. Otherwise, there are some other terms. But if they're independent, we only have to add the two power spectra. Okay. So we add the two power spectra, and we know which one is. So, which are the two terms that we have to add. And there is something interesting here. That is, in this plot, you may see that there are some frequencies, these ones, where you have more power coming from the signal, while there are some other frequencies where you have more power coming from the noise. And yeah. Now we can see the same effect, but now in 2 dimensions. So we have the power spectrum of the original image. So now we are not taking a profile anymore. And the power spectrum of the noise. And then the power spectrum of the addition of the two. And now we highlight which is the area, which are those frequencies, where we have more noise than the signal. So all these points, blue points, they have more noise than signal. And this is the opposite. We have more signal than noise. So the signal to noise ratio in this area, in this red area, is larger than 1. In the blue area was smaller than 1. Okay, so now we superpose 2. And yeah, this is another example, same idea. Nothing new here. Okay, and now you understand why a low-pass filter is a good idea in many of these applications. So you may design a low-pass filter. This is the cutoff frequency. And we have highlighted here the points where you have more signal than noise. So by low-pass filtering, if you choose appropriately the radius, you would keep those regions where you have mostly power coming from the signal. You see? While you are leaving out all those regions, all those frequencies, where you have more power coming from the noise. So a low-pass filter is a very good idea for this reduction of noise. Okay, so this idea. Now you know already low-pass filters, so we have used the Gaussian low-pass filter. And yeah, so it is blurry, but it has less noise for sure. So depending on what is your application, you may prefer more blurred images, but with less noise. Okay, then another example. What if we knew exactly the frequencies at which we have signal to noise ratio larger than 1. So we could design a filter that is taking exactly these red points. The problem is that in reality we don't know. But what if we could know? Then we could remove all the pixels out of the red area, so we remove the blue pixels, and this would be the result, which is much better than the low pass filter. But the problem is that in reality you never know which ones are coming from the noise, which ones are, or in which frequencies you have more power than signal power than noise, or more noise power than signal. And this is a comparison of the two. Okay, so this is preserving very much the edges. It is also a bit more noisy, but it is preserving better the edges. Okay, that is if our model doesn't have a point spread function. So we were saying my noisy image is just one clean image plus noise. What happens now if I have a point spread function? So how do I design my filter? Yeah, the point spread function, you know where it is coming from. It is just the blurring caused by perfections in the camera. All this part, you know better with observation. Okay, but the effect we already know what it is. So you have a clean image, and then it is convolved with this power point spread function. Then it is blurred a bit or a lot, depends on the point spread function. Like this, we will not enter. Yeah, this is a graphical representation of that process. So you have the clean image, you have the point spread function, then you have the convolution of the two, and then you have noise. This noise is not affected by the point spread function. And this is another interesting point. So this is, say, let's make it change colors. Okay, so this is the image formation model. Image formation model. And we have seen a way of removing noise from this model, that is this low pass filter. Okay, now we have changed our model to something else. So we have J is I involved with the point spread function plus noise. Okay, in this model, let's say that the noise is always uncorrelated. It is always white. Okay, so this is another image formation model. And this noise here, this is white. Okay, let's put another image formation model. So the image formation model is something that you need to know in every application. So you need to know how your images are formed. So, for instance, in electron microscopy, we have this one. We have some noise, let's call it 1, both with H, plus some noise 2. And both are white. Okay, so this one is white, this one is white. But what about, I can rewrite this in this way. So this is I convolved with H, plus N1 convolved with H, plus N2. So you have now two sources of noise. This one is white. This one is white. What about this one? Is it white or not? What do you think? Noise that is convolved with something. Is it white? It is not. Okay, so let's think what is white noise. Okay, so we have it here. I don't know where. We have it here. Okay. So white noise means, given a point, you cannot tell anything about the nearby points. What happens with the convolution? The convolution is, to compute a point, you have to take the nearby points, make some calculation, and that is the output. So given a point in the output, I can tell you something around the nearby points because they were used to produce the output at that location. So it cannot be white. Okay, so let's try to formalize that a bit more. Let's try to formalize that. Okay, so let's concentrate in this term now. Okay, so we take this term, take it out. Okay, and now we have N1 prime is N1 convolved with H. What is the power spectrum? What is the power spectrum of N1 prime? It is, and this you know already, it is the power spectrum of 1. This is y. But now multiply by h, our frequency now, squared. Okay, so this one is y. This one here is y. And this is the CST of N1. That depends on omega. This one is not. Okay, so this one, let's say it is a low pass filter. So it is a low pass filter, and it is like this. Now what we shouldn't be here. So annoying. So now the combination of the two is this thing. This thing. Power spectrum is N1 prime. There is no omega. This is the axis of axis. So let's put numbers. So let's say this is sigma squared, this is 1, and then this will be sigma squared. 1, 0 outside. Okay, so the power spectrum density of colored noise is not white. It can be whatever, but it cannot be flat. And then, as we said, you need to know which is your image formation model in each one of your applications. So these are 3 different image formation models. And we have seen that a good tool to remove noise here is low pass filter. And we will study now a good tool to remove noise in this image formation model. Okay, so let us see. So we want to remove noise from this model. Okay, so we take the Fourier transform. So if you take the Fourier transform, then the convolution becomes a multiplication. So you have the Fourier transform of J is the Fourier transform of I times the Fourier transform of H plus the Fourier transform of the noise. This is the same model, but now in the Fourier space. Okay, now let us put names. So we have this product, I times H. We had it before. Okay. This is a mistake. This is H. So we have I times H. So we have this image. That is the clean one that we want to recover. And even we want to undo the filtering. Okay. And then we have that convolved image that is added noise. Okay, so we have here this addition. Okay, good. Then I will try to I will try to recover K by filtering J with a filter W, but I still don't know which one it is. Okay, I have to decide which is the filter W. And once I have an estimate of K, so this tilde here means an estimate. So once I have an estimate of K, I can have an estimate of I by simply dividing by H. So my estimate of I would be J filtered with W divided by H. Okay, and then what I want is that my estimate of I is as close as possible to I. I is the ideal image. So I want to recover from the image J, this is the one that has noise and a convolution. I want to design a filter W, that I still don't know which one it is, that the estimate of I is as close as possible to I as I can. So this is a least squared problem. So a least squared problem, let's solve it. Okay, so here we have the solution. So the solution is this W. Okay. And let's look at it. Okay, so we will write it outside. Let's make some space. Let's look for some space. So we are here. Okay, so we say W. I will drop the frequency. So it is H star. So this is complex conjugate times times the energy of I. And then here we have H squared I squared plus noise squared. Okay, so let me check that it is true. Okay, so now let's reorganize this in a different way. Okay, so let's reorganize this in a different way. So I will divide by, so this is the filter complex conjugate, and then the power spectrum of the image. And now we have the power spectrum of the filter image plus the power spectrum of the noise. Okay, so let us divide by I squared. Okay, so this would be H star, and then we have modulo H plus this divided by this. What is this? We have a frequency everywhere, but I don't want to make it too clumsy. Okay? So what is that? That is 1 divided by the signal to noise ratio. You see? It is the signal to noise ratio. The signal to noise ratio also depends on frequency. Okay? Normally we don't write it, but it depends on frequency. So we can rewrite this. Write this as H plus 1 over the signal to noise ratio. And let us think so let us think that we don't have any noise. So I have noise equals 0. I don't have noise. So what would happen? So the signal to noise ratio would be what? If noise is 0, this is 0. Okay. And I will have h divided by the modulo of h. But the modulo of h is h times h conjugate. So these two cancel. And what I have is 1 divided by h. Does it make sense or not? So if you look, let's go to here. Let's say that you don't have noise. So if you don't have noise, this image is equal to this one. What is this one? This is I times h. So if you don't have noise, the best thing you can do to recover I is to divide by h. So it behaves in the way we would expect. Okay, so this is on one branch. Okay, so let's make 2 branches. So in the first branch, we don't have noise. So I will delete this one. And put it here. Here. This is n is equal to 0. Okay, so what happens if I have a lot of noise? I have really a lot of noise. What is the best thing you can do? Set it to 0. You have so much noise. So n goes to infinity. Infinity plus something is infinity. And something divided by infinity is 0. So the best thing, if you have really a lot of noise, the best thing you can do is just put a 0 there. So your image has been spoiled at that frequency because you have really a lot of noise. There is no way that you can recover it. So this formula here, behaves somewhere in between the two states. So where you have very little noise, you are mostly dividing by 8. Where you have a lot of noise, what you are doing is just okay, set it to 0. So this is halfway in between, okay, depending on how much noise you have. And then the problem is transferred to estimate this term. You need to estimate what is the signal to noise ratio for every frequency. Let's see time. Okay, good. So yeah, I think this way of reasoning that I showed you, I think is a bit better than this discussion here. Okay, so how did we come to that? How did we know that this is the best filter you can have? Okay, so because there is a problem that we want to minimize something. Where I don't know. I don't know what is the true image. If I know what is the true image, I don't need a filter to recover it. Okay, so how can I design a filter without knowing what is I? And the trick is this one. You don't need to know what is I, but you need to know what is the power spectrum of I, which is much weaker condition. Okay. So let's see. Okay, so we can start deriving it, and at some point we will make a jump because that gets too complicated. But let's follow the beginning of the reasoning. Okay, so what is I? I is k divided by h. So k was this one. K was this one. So I is k divided by h. Very good. And then what is my estimate of I? My estimate of I was j, that was the final image, with my filter W divided by H. Okay, so now you have in the denominator, in both denominators you have H, so you can take it out. You have to take it out with the module, okay, and it is dividing, so you put H to the minus 2. And what is J? J was K plus N. Okay, good. Then you develop this term, expand it, and then you have K times 1 minus W. Okay, so this is these two terms come to this one, and then W times N. Okay, good. Now you have a module. So if you have a module, it is the first, so the argument of the module, and then the argument complex conjugate of that module. Okay, so we have this term, and then the same term complex conjugate. Now you multiply everything. Okay? Well, the complex conjugate, you know, the complex conjugate of an addition. So there are two properties there. So if you have the complex conjugate A plus B, conjugate, this is A plus B. And then we have A times B conjugate, this is A times B. Okay, so you apply that. You apply that to here. And then you multiply everything, so you have the multiplication of two terms, so you multiply everything. Okay, so what do we have here? So yeah, you would start getting, so this term times this term is the complex conjugate of that, is the modulo of that. Then you have this one times this one, you get this one, and then you get these two cross terms. Okay, so what do we have? So we have this one, then this one that goes there, and then we have here something times the complex conjugate of something else, and then that something else without complex conjugate times the complex conjugate of this one. Okay, so let's see. So this term is the complex conjugate of this one, you see. And if you have one complex number plus the complex conjugate of that complex number, what do you get? Twice the real part, because the imaginary part cancels. So you have twice the real part of this thing. Okay, and then we have an integral of all these. And an integral of all that, this is we are integrating in frequency. We can separate in two integrals. So the first integral with these two terms, and then the other integral with this one. Okay, okay, so this is just copying the last equation. Okay, so let's look at this equation. This equation is this K, we have K divided by H squared, but K divided by H was I. Do you remember? So this is I, and then I have used one of these H, so I have only one H left. Okay, so I have some filter, another filter, so a lot of filters here, then I times N. But we said at the beginning that I and N are independent. What does it mean that they are independent? That this integral is 0. Okay. So if that integral is 0, we have almost that integral with a little bit of filter. A little bit or a lot of filter. But if this term without the filters are 0, probably with the filters too. Okay, or they must be close to 0. Okay, so we forget about the second term. And then, So this is just rewriting whatever is left. And yeah, this k we can now make the same trick as here. So k was I times 8. So we can take only substitute k by I. Okay, and then we have used one of the h's there. And now it is where we have to make it here, because that gets too complicated. So we want to minimize this. So let me write that. So I want to see this one. So we have that epsilon squared is equal to the integral over frequency of 1/8 volts. And then we have I 1 minus W. So the module of I and the module of 1 minus W. That's W. Okay, and if we want this to be minimum. So I want this to be minimum. When you want to minimize something, what do? You have to differentiate that with respect to omega to W. So we want to find the filter that minimizes that. So what I have to do is compute this with respect to omega, but to with respect to the filter. With respect to the filter. And equate it to 0. And that is where it gets complicated, because all these are complex numbers, and we don't know the differentiation rules for complex numbers. Okay? So, but if you know, you can compute the derivative of that with respect to 0, and you can solve for W. And that is what we have done here. But you see that the same kind of terms appear. So we have, what are the main terms here? We have H, we have the power spectrum of I, and the power spectrum of N. And those are the ones that appear here. There is nothing else. So you don't know to need I, so you want to minimize something that you started formulating with I, but you don't need to know why. You need to know the power spectrum of I. But that is easier. And now we will see the results. Before we make a break, a minute. So let's continue. So let us use this formalism of the Wiener filtering. Okay, this derivation, by the way, is called the Wiener filter. Okay, this filter W is called the Wiener filter. That is why it is called W. Wiener. Okay, so let us use the Wiener filter to denoise images when there is no filter, H filter, so there is no point spread function. Okay, so we have the same situation as before. So we have the image, the noise, and this would be the addition of the two, and the same in the power spectrum. And this would be the Wiener filter. Okay, so this is this calculation that we had in the slide. So this H star divided by modulo H, modulo H squared, and so on. So you see that it is much richer than a low pass filter. So a low pass filter would be just a circle. But this is much richer because it has, first, it extends to regions where the low pass filter wouldn't have extended. So all these lines, they are recovered by the Wiener filter, and they were not by the low pass filter. And also, it is not flat. So the low pass filter is just 1 and then 0. But this is not flat. It has a variation. So if you have more energy, if your signal to noise ratio here, so this filter here. So if your signal to noise ratio in a particular frequency is high, then it looks more or less like 1 over H, but in this example there is no H, so H is 1. So it looks more like 1, where you have a lot of energy. But as your signal to noise ratio decreases, then you are going down to 0. So you have variations. In some regions, here in the middle, it will look like 1. But as you go away, it will go smoothly to 0. So it is not just 1 or 0. It goes with a smooth transition, and it recovers many more regions than the ones recovered by or kept by a low pass filter. So yeah, the spectrum of the Wiener filter image, the original image. So you see that they are pretty similar, and these are the images. Okay, so that is the noisy one, and this is the Wiener filter. So the Wiener filter is really good. It's really, it preserves the edges, because the edges, you know, they're coming from high frequency components. The high frequency components are the high frequency components are kept. And then it has very little noise. So really the Wiener filter is something, okay, and this is just a comparison between the two. And you can compare to the Gaussian low pass filter and the Gaussian low pass filter. Okay, and now let us say that there is a Gaussian, so H, the degrading filter, so the point spread function, is a Gaussian with sigma equal 2. So yeah, that would be the original image, that would be what you recover, so what you measure. So that would be the Wiener filter. And the Wiener filter, you see that at some point it goes to 0. Okay, so let us look at the formula again. So let's forget about the signal to noise ratio. Okay, so let us say we don't have noise. Let's concentrate on this part. So let's say that we are in that situation. So, and that our filter is like this. So let's say that H is a function of omega, is a Gaussian. Okay, this is omega. Okay, so let us look at one of these points very far in the spectrum, so that the H is almost 0. Okay, so the filter, because we don't have any noise, we have this ratio. But this is 0 divided by 0. You see? H star at that location is almost 0. And the modulo of H is also 0. So, but you remember limits when you were in first year of calculus. Okay? The limit of this when H goes to 0 is not infinity, is 0. So when you go very far, the Wiener filter doesn't explode. And it doesn't explode because of this term, this one is controlling. So this alone would explode, but with this addition, it doesn't. Okay. So it goes to 0, and it makes sense if sigma is such, so the point spread function is such that, don't see the time. Okay, so if the point spread function is such that it has completely killed the high frequency components, and we can see here. This was the original, this is what we measured. So you see these lines here, they have been completely killed. So if they have been completely killed, what is the point of trying to boost them? So there is no point. They have been killed. They have been killed. Just leave them to 0. And then, but then still, you can recover it a bit. So you see that it is a little bit larger than this one. You can recover them a bit, not to very high frequency. And here is the comparison of the two spectra. And this is the final result. Okay, so now it is blurred, so it cannot do magic. So if a point spread function is completely killing some frequencies, the Wiener filter cannot recover it. There are now ways to recover them, but Wiener filter is a linear filter, right? So a linear filter is simply multiplying whatever is there. So if you have a 0, 0 multiplied by whatever is 0. So you cannot recover it. But now there are ways that are non-linear filters. So you may learn how natural images look like and try to fill that frequency with something sensible. And that is the next paper that you have, that is deep learning. So deep learning is a tool that now it is used to do this kind of things. Okay, so yeah, another comparison of the two, so that you can go, you can go from one to the other and compare them. Okay, so what about in practice? Because in all this simulated data, we know what is the point spread function, we know what is the power spectrum density and so on. But if you have a single image, how do you apply this? Okay, so you have to find your ways. Okay, so let's say that you're given this photo, this picture. How do I estimate the sigma? What is the power spectrum density? So you can go to a very flat area. In a very flat area, there is no signal by definition because it is very flat. So whatever you have there is just noise. So you make a sum of that area and you estimate the noise from that. Okay. And how do I estimate the noise? Okay, so let's say that there is a very smooth variation in the background. So you already know this kind of tricks where you can, so I want to estimate what is the noise. The noise, assuming it is flat, it has 0 mean. So if it has 0 mean, one possibility could be, okay, you take the original image, you blur it with Gaussian that is very wide. So very wide Gaussian in Fourier space, what does it mean? So we are here. We have a spectrum of that area. Okay, so we have that spectrum. That is the power spectrum density of that area. This is only. I do it always in 1D because I can make it, but in these things apply to dimensions. Okay, so I have some spectrum there, and I would hope that it's kind of flat. So I would hope that it is kind of flat. It might be that, especially, it needs to have zero mean, and if you have a flat area with some color, it is not zero mean, it has some central value. So how can I get rid of that central value? I can multiply with this filter. That is 1 everywhere except this point that is 0. So this 0, this is the filter. So this 0 is giving the 0 frequency, that is the mean. So I want to remove the mean. How can I do that? Okay, so I can, so I have an input image I can subtract I involved with the Gaussian G. This in Fourier space, let's make it. So this in Fourier space will be, okay, so I will write this as I involved delta minus I involved T. But that is equal to I involved with delta minus T. That's delta. Now let's do the Fourier transform. So now we do the Fourier transform. So it will be the Fourier transform of I times this inverse Fourier transform. What is the inverse Fourier transform of delta? It's 1. And then the Fourier transform of T. And this is what I have. This one here. This one here is this one. 1 minus the Gaussian. And we knew this from the high-pass filters. Okay, so let's make a high-pass filter with this Gaussian. And then you estimate what is the sigma in each one of the channels. Okay. So now I know the power spectrum of the noise. Now I have to look for the point spread function. So you look for something that looks like a point. So in that glass, there is a bright point. So you make a zoom, and you take the numbers, and you make these numbers to add up to 1, because otherwise they would change the mean. And this is the pH. This is the point spread function. Now you know both things. And now you can compute everything. You know what is the point spread function, and you can compute what is the Fourier transform of that point spread function. And you have also the spectrum of the noise that you assume to be flat. And you need to know what is the spectrum of the power spectrum of I. But you cannot say, okay, I don't know I, but I can approximate I by my observation of I. So I can say, this is power spectrum. This power spectrum of the original image is the power spectrum of my eye. And then you have everything. You can design your filter. And then you apply it to your filter. So this was the original. This is the filtered one. That, from the distance, you barely see the difference. You need some zoom. Okay, so that is the original filter and the MATLAB Venus filter, the implementation of MATLAB. And this is the filter that the guy did. You see this a little bit more sharper here around the eye. Phrases are a little bit sharper too. So any question? So knowing the power spectrum of the the ideal image is not that atypical. So you normally may know. Okay, so that was a denoising for uncorrelated noise. Now let's do it for correlated noise. So now we will have noise that has a correlation that is not a delta. Okay, so and here you have an example. So an interference, for instance, you may have I don't know, an electromagnetic interference that is interfering with your camera, and then you may get this pattern. And if you know one pixel, what is the value of the noise at one point, you know immediately what is the value of the noise somewhere else. So you see the correlation there. Okay, so one possibility would be, okay, I will do blurring along the direction in a direction that is perpendicular to the pattern. So the pattern goes this way. So I will make a blurring there. And it is true that you remove the pattern, but you also remove many features of the image. Okay, so you convolve with this and you kill the pattern, but you are also killing the image. Okay, so let's look at the power spectrum. So that is the original image. This is the spectrum of the image plus noise. And when you make a zoom, you see that there are two bright spots there. Does it make sense that we have two bright spots in this case? What do you think? Why do we have two bright spots? That is a sign. You remember the wavelet, the Fourier transform. The Fourier transform, we have this kind of waves. So this is a wave. And it is a wave. Its Fourier transform is a couple of deltas. So we see there a couple of deltas. And now we can design our filter. So you look at the spectrum, and we already know this trick of making one everywhere minus, and we subtract this Gaussian. So this is the same as this one. We're doing the same trick as in here, but now we have shifted to somewhere else. So instead of just killing the zero frequency, we are killing one particular frequency. So this is our mask, so our filter in Fourier space. And this is the mask power spectrum, so multiplying the input image times the mask. And now this is what we get. So it is clean everywhere except at the borders. Why the borders? Why the borders are special? Because of the periodization of the Fourier transform. You may remember that Fourier transform assumes that the input image is periodic. So we are repeating this one. We are repeating this image everywhere in space. So we are putting it here, there, 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 there. We are repeating it infinitely many times. And then there is a discontinuity here in the border, because we are coming from blue, so we are blue, 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 and at the border it becomes white. So that is a discontinuity. And because of this discontinuity, we see the convolution of the filter. So if you make the inverse Fourier transform of this filter, you will get something, some impulse response. So you see the convolution of that impulse response with this step function that you have here. The same happens on the other side, right? It is not so easy. Here is MATLAB code to do that. And then there is a lot of discussion that I don't find it so interesting of how to translate coordinates into so indexes in the Fourier transform into frequency. So you may remember this kind of discussion that we had also when we would define a Fourier transform. So given that you see a pair of coordinates that you are interested in the Fourier space, how did you translate them into frequencies? But we did all those reasoning saying when we introduced the Fourier transform, so I don't find them so useful now. So you see the same kind of equations that we had at that time. Same kind of equations. Okay, let's go to this one. You may remember the printing. You remember this thing where we had sets and all that. Okay, so in that application, we have some patterns. So and these patterns are made of the multiplication or the addition of different waves. So let's say that you have this wave, you would have this couple of deltas. You have this wave, you have this couple of deltas. And now if you have this pattern that is the addition of the two waves, you have these 4 deltas. When you have this, the same happens with other orientations. Okay, so when you have these patterns to print, what you are having are deltas. Now, the different colors, they have a different orientation of the pattern. So we have the same pattern, but now in different orientations. So this is the pattern for the black color, yellow, magenta, cyan. And then you are adding all of them, because you are printing all of them together into the same image. So your power spectrum will be made by the patterns of each one of the underlying colors. And this is what you get again. Okay, so yeah, this we know how to print. Okay, so you compose your image into your bases, color bases, and again here you remind all this. We have the RGB base, but this CMY is another base, and it is a change of bases in the color cube. And then you take your pattern, you print, but at the end you have the addition of all these. So this is just a reminder of how we were printing. Okay, so now let's say that you take a printed image and you scan it. Okay, so now you have a printed image. You want to put it back into the computer. So you scan it, and when you go to the details, you see these rosettes again. Can we get rid of those? You do the Fourier transform. You do the Fourier transform, and this is the power spectrum of that image. And you see a lot of bright spots. And those bright spots, here we are showing multiple Fourier transform at the same time. So you decompose this into the RGB components. And this is the Fourier transform of the R, the D, and the B. And you see these bright spots. Okay, I can. This is a mistake of the printing. This is this symbol should be sigma. So now you combine with a Gaussian of sigma equal 1. So sigma equal 1 is a very narrow Gaussian. So in Fourier space it is very wide. So you barely see much of a difference. Now this is sigma equal 2. This is sigma equal 4. Sigma equal 8. So it is true that you get rid of the rosette. See, the rosettes here, they're very visible. And the more you filter, the more you get rid of them, but you also get rid of the details. Okay, so let's see if we can design a better filter. Yeah, this is the same, but now looking at the differences. Okay, so this is the original. This is the blurred one with sigma equal 1, and the difference between the two. And with sigma equal 2, sigma equal 4, sigma equal 8. So in the difference, you see the rosettes. That is what we want to get rid of. So that is good. But you also see a lot of details of the image. So you have lost all these details, and that is what you don't want. Okay, but so let's design a filter that takes out the specific pattern. Okay, so we have this Fourier transform where we have peaks in the Fourier transform. So I can design my filter in this way, just to remove the peaks. And this is a 0-1 filter, so it is a 0 there, 1 everywhere else. But you know that having these are very hard transitions, going from 0 to 1 very quickly. So you know that causes ripples. You remember the low pass filter, the ideal low pass filter, so that causes ripples. So let's smooth that. So you convolve this one with the Gaussian. And now you use this one as a mask. You multiply, and then you that is the filter image. Still, it has a few of the patterns of the printing pattern. When you remove the first peaks, second peaks, third peaks. These are the differences. So now we are getting rid of only of the patterns. See, this is with the first, so the first mask, this one. We're taking away the pattern. With the second, the third, so we are removing more and more details of the pattern. Yeah, this kind of filters, where you remove a specific frequency, they are called notch filters. Okay. Any questions? No? Okay, so we move on to the next kind of filtering. That will be medium filter. So the medium filter is the first nonlinear filter that we will see. And it belongs to the family of morphological filters. And there is something interesting in nonlinear filters. That is, okay, so let's say that you have an input image I goes to some restoration filter, let's call it W. And then we have WI in Fourier space. So all this is Fourier space. All this is Fourier space. Okay, but in Fourier space you are multiplied by something, and it is this reasoning that we did before. So if my I, the spectrum of the I, sorry, this I, power spectrum of I, that depends on omega. So let's say that you have an image, it has whatever spectrum, but at some frequency it has been deleted, and then you recover it. So there is no filter W that can recover that thing, because all I can do is multiply by something, and if I multiply by 0, I get 0. So there is no way that I can fill it and do something like this, or something that is more smooth. doesn't go to 0. Yes. With linear filters, this is impossible. So let's move on to non-linear filters. And here you have an example of what we want to achieve. So let's say that you have a noisy image like this one, and then you want to denoise and have that result. And the median filter actually is very good at two things. One is that dealing with flat areas. Flat areas, they are very much denoised. And the other one is at keeping edges, and we will see why. Okay, so how it is defined? So, yeah. So you have to define a neighborhood, and these neighborhoods, they can be squares, but they can be whatever. So here we have a funny neighborhood. So you want to process this point, and now you have the point and the neighborhood. You have the values there. So these are matrices of numbers, so you take the numbers. And you take all those numbers, you sort them, and you compute the one in the middle. That is the definition of the median. So the median is a value such that half of the observations is below that value, the other half is above this value. Okay, and then you move to the next point, and you repeat the same process. So, yeah, that is what is explained here. So, you take the median of all the values from the locations Q, where Q belongs to the support of P plus this neighborhood. Okay, so this shape here is your neighborhood. It is the set in that equation. What is the support? The support is, well, we have to move your neighborhood to the location P. Okay. So that is expressed in that way. Now, what is the support? The support is the region where this neighborhood is different from 0. Okay, so outside, the neighborhood, the mask itself is 0, and inside, the mask is 1. So we take the support, and then we take the median. We take the median of all the values of the image I, where Q is there. So it is simply just a way of writing. And then you move to the next location. Pretty simple. Okay, let's do it in 1D because it is simpler to show. So let's say that we have a noisy step. Okay, so there is a function that is this 0.25 and then 1.25, and there is a step function, but we get a noisy version of that. So we get just this noisy version. Okay, so we do a linear filter. So a linear filter, for instance, we convolve with that. There is a mistake in here. It goes from -4 to 4. So we take the input, we convolve with this, and this is shifting. This is just a moving uplift, so it is a linear filter. So this is the result, okay? And we understand why we get this smooth transition. So at the beginning, we are computing the average of 9 samples. So the average of 9 samples, okay, it can be noisy. Right? This is the average. The underlying signal is always the same. So it is always the same, always the same. But then at some point, our filter gets values from the left of the step function and from the right of the step. So we are computing the average of low values with the average of high values. It's annoying. Okay, so we are computing at some point, we are mixing low values with high values. And then that is why we get this smooth transition. It goes smoothly from low to high. That is expected. And then we are again inside the high values all the time, and then we get a little bit of noise, but okay, that's fine. And then we are getting out of the noun signal, so that is why it drops to 0 again. Okay, so at this point, so just one sample before the step, we get we have five values from the low part and 4 values from the large part. One sample after. So one sample after that, we have 4 samples from the low part and 5 from the other part. Okay. That is when we compute the mean. When we compute the median, it's the same. We also have 4 and 5. But you see that the result, it has now a much sharper edge. Why? Because when I have these 5 values from the low part and I sort them, I get the low value. When I move one sample to the right, I now get 5 samples from the high part. I sort them and I get this one, 1.0. You see? So this sorting and this median is very useful when you have edges, especially when compared to the mean. When compared to the mean is just averaging, while this sorting makes you take one of the values from either side. And here we have the comparison of all the results. So we have the underlying signal, we have the noisy observation, we have the one computed with the average, that is the green, and then we have the one computed with the median. And we see that the one computed with the median, it has a very sharp transition, but it doesn't go smoothly from low to high. Okay, so another comparison, the same thing. Okay, so let's apply this to binary images. So let's say that we have a binary image, like this one. So binary is either it is 0 or it is 255, or 0 or 1, whatever 2 values you like. You do this process of moving a neighborhood, and within the neighborhood computing the median. This is what we get. This is fantastic. Yeah, so yeah, this is noisy, this is the original, this is the median filter. The median filter is really good. Okay, so now let's have grayscale images. So with grayscale, okay, this is the noisy one, and we will we will compare the linear filter with the non-linear filter. For this here, we have a filter with a kernel that has a 3 times 3, and this will be a 3 times 3 but median, not average. Okay, a median looks better, but now you apply it again on both sides. Again and again, and after 10, see that okay, this one I would say it is less noisy than this one. But it is also much smoother. We don't have edges anymore. And let's say that you keep doing to infinity. So you apply this filter many times. So this is with 10. You apply it many times, you get a constant. Does it make sense or not? And with the median, it converges to something that is called the median root. Does it make sense that we get a constant?
If there's the average between all the pixels, so we can at one point, instead of comparing only the inputs, let's start comparing all the pixels of the image. So
yeah, but the kernel is all the time the same, 3 times 3. So the kernel doesn't change.
Yeah, but if you start repeating all the times the process, it will at the end giving the average of the parts.
Yeah.
It will start doing the average of the average of the average of the average.
Yeah, that's one way of thinking, and it is correct. So that is thinking in real space. What about if we think in Fourier space? So let's say this is our Fourier space. And we apply 1 time the filter. So we have this filter that it is very narrow in real space, so it has to be wide in Fourier space. Okay, so let's say this like this. It is very wide in Fourier space. And this would be the first application. So you know that we are multiplying the power spectrum by times this. Okay, now I do the second application. My second application will be red now. Okay, so what is my filter? So the first application is h squared. My second application is is h to the 4. This is my second application, and h to the 4 has to. This is 1. And if you multiply a number that is smaller than 1 to the power 4, it is smaller than if you power it to the power 2. And now the third application. The third application is this one. 6. Now it will be like this. And you keep applying and applying and applying. And at some point, look, you have H infinity. And H infinity is just a delta. So a delta is just keeping the average. So one way of thinking is in real space. The other way of thinking is in Fourier space. So it makes sense that a linear filter, when applied multiple times, converges to this kind of deltas. And in this particular case, a delta at low frequency. But the median doesn't happen. For the median, it converges to something. Converges to this thing that is called the median root. Okay. And this part is only explained. It is not showing why. Right? This is explaining that if you take a linear filter and you convolve many times, at the end you get a constant. And if you take an image, you apply a median filter many times, at the end you get something that is not a constant. But it doesn't show why. This is the MATLAB code for that. Okay, so I think it is a good time to make a break. We will continue next week. Tomorrow we have practice.